Now, there might be some confusion when you compare discussions of toughness for non-ceramic materials with toughness for ceramic materials. You might have noticed in looking at other materials such as tooth enamel and dentin, or materials such as brittle metals versus ductile metals, or looking at polymer-based materials. You might have noticed in any of those classes that strength and toughness don't necessarily go hand in hand. In fact, quite often, the stronger material will be a material that is more brittle or not so tough. An example here is tooth enamel. And we're looking at a graph of the stress on the y-axis, which is force divided by area. On the x-axis, we have strain, which is the change in the size of the object divided by the original size. So that's a percent stretching on the strain axis. And we have the stress, the y-axis, will determine the strength of the material. If we pull on the material up to the point where it fractures, then the level of stress that it fractures at is the strength of the material. So tooth enamel, according to this graph, has a higher strength than the strength of tooth dentin. However, the toughness is related to the area underneath this curve. So if we drop a line down here and we shade all the area under the curve, and if we do that for tooth enamel too, what you will be able to probably estimate is that tooth enamel has less area under its fracture curve than dentin does. And so dentin would be the tougher material, can absorb more total energy before it fails. But tooth enamel is the stronger material, actually goes to a higher stress before it fails. Now in ceramics, this is never the case. In ceramics, toughness and strength go hand in hand. Well, actually, I shouldn't say never. As soon as you say never, you can think of at least one example. I know of one type of, rare type of ceramic where toughness and strength are not related to each other. But for most intents and purposes, and for all ceramics we currently use in dentistry, higher strength means higher toughness, and higher toughness implies higher strength. In red here, I'm showing the fracture curve of a very strong, tough ceramic. In blue is the fracture curve of a less strong ceramic. And you see the difference is that the stress strain curve for a ceramic material never bends over at all. It remains linearly elastic. It follows a straight line all the way up to the point of fracture. For all ceramic materials that we are currently using. And so if it has a lower strength, it doesn't go as high on the y-axis, then it will have less area under the curve also. Okay, so we talked about this Y factor that factors into the stress intensity factor, K. And we talked about how Y is higher for a sharp crack. And I mentioned previously that ceramics are brittle because even though they have dislocations in their crystals, that these dislocations cannot move. And so the lack of dislocation movement, the lack of plastic deformation, leads them to be brittle materials with cracks that remain sharp in them. So why exactly does that happen? Why does a lack of plastic deformation lead to cracks being sharp and growing sharper as the crack grows through the material? To help illustrate that for you, here is a cartoon depicting the way a crack goes through a metal material. And you see this crack has a force being applied to it, and ahead of the tip of the crack, the dislocations are moving and allowing the material to plastically deform, and it's opening up these microvoids ahead of the crack tip. And as the crack grows and stresses continue to be applied and cycled, these microvoids open up larger and join up with each other and join up with the main crack. And so the crack always has a blunt void ahead of it to grow into. Since that doesn't happen in ceramics, ceramics only grow by the tip of the crack tearing through the atomic bonds of the material just ahead of them. And so that crack will get sharper and sharper as it grows. And Y tends to be much larger for ceramic materials. Okay, flaw sensitivity. We mentioned that the strength is dependent on the size of the flaws present, and I want to describe a little bit better why that is also. The fracture toughness, K1C, or the critical level of stress intensity factor at which the material fractures. For almost all ceramics materials, the fracture toughness is a constant for a given microstructure of the material, given composition. And so if the left side of this equation is a constant, and we have on the right side of the equation the strength of the material, sigma sub f, and the size of the flaws that are present in the material A, then if we increase the size of those flaws and A becomes larger, then sigma sub f, the strength of the material, will have to become smaller in order for K to remain constant. And then if we reduce the size of the flaws by careful processing or by polishing the surface of the material, then the flaw size A becomes reduced, and then the strength has to become larger in order for that fracture toughness again to be constant and for the equation to remain true. Okay, here is an example. It's a dental crown. It's a finite element computer model of a dental crown. And it was constructed in the research group of Dr. Ken Anasavis, who is the author of one of our textbooks, and incidentally was my professor for my graduate studies at University of Florida. And his computer model is showing a color map of the stresses in a dental crown. This is the outline of the dental crown, a portion of the dental crown here. And this is the crown preparation. This is the dentin remaining on the tooth after the unhealthy tissues have been carved away, preparing it to have a crown cemented on top of it. And what we find is if we bite with a force here, that the point of highest stress is colored by the computer as being red in this region here on the cemented surface of the interior of that crown. Now, this isn't the case for all fixed prosthodontics. Depends on the structure of the layers in the crown, whether there's more than one material making up the crown or not, and the situation is very different for bridges or fixed partial dentures with multiple units connected together. But what we see is that the surface at the point of high stress is like the surface of most materials. It's covered in a variety of types of flaws. We have some small and some large pores on that surface. We have some pores in the interior, just below the surface, and we have some small and some large scratches on the surface. And the weakest link theory tells us that if there is a distribution of different sizes of flaws along the surface and subsurface of a material, that all that matters is the one largest flaw. Weakest link refers to the strength of a chain. You can imagine a metal chain of links, and one of the links is not quite as strong as the rest of them, and the strength of the entire chain is not going to be the strength of the average link in the chain. It's going to be the strength of that one weakest link. All it takes is for that one link to break and the entire chain is broken. And that's the way ceramic materials work also. If there's a distribution of flaw sizes at the point of high stress, then the largest flaw there is going to control whether or not the material fails and how long it lasts before it does fail. Since we have a distribution of flaw sizes with some ceramic components containing a large flaw at the point of high stress and some containing a smaller flaw at the point of highest stress, we'll also have a distribution of strengths between those components, because, as we discussed before, a large flaw leads to a smaller strength, and a small flaw in your material leads to a larger strength for that component. And so there will be some variability in how long a ceramic component can last before it breaks. It will be very important to you to be able to read publications in the technical literature and compare different ceramic products that are coming to market and decide which ones have more predictable lifetime for your patients and which ones will have a longer lifetime. Hopefully find one that has a long and predictable lifetime. The type of graphs that are used in those publications are sometimes different from the type of graphs used for other data. They have a special type of graph called a Weibull graph, and it describes this asymmetric distribution of lifetimes or strength values that ceramic parts have. It has a really strange y-axis. Shown here is the natural logarithm of the natural logarithm of 1 over 1 minus p, where p is the probability of failure at a given stress level. And on the x-axis is the logarithm of the stress level, or the logarithm of the time that you wait to see if it's going to fracture under a constant stress. And so when transformed onto these strange axes, it turns that distribution into a straight line. And the slope of the line tells you something about how predictable the lifetime or strength of that particular type of ceramic component is. If the slope is very steep, like the line shown in red here, then that means that there is not much variability in the strength of those components. And if the slope is less steep, as shown by the yellow line there, then there's more variability, and it's difficult to predict for any given patient's prosthesis, for example, how long that prosthesis will last if it's made from that material and made using that processing method. The slope of the line is called the Weibull modulus, and it's often represented by m. Sometimes it's also represented by beta. And the slope in the case of the red line is 7. In the case of the yellow line is lower, 4.6, indicating more variability. Now, how that relates to a bar chart that you may be more used to reading, you can look at the standard deviation. The standard deviation on the red group is very small. So a small standard deviation bar is similar to having a steep line on a Weibull chart, and the standard deviation for the yellow group is quite large, and so a large standard deviation or large error bars is the same as having a less steep slope on the Weibull graph. Now, how do we decide on average which component is going to last longer or be stronger by looking at a Weibull chart? You'll notice that the average